Welcome everyone and thank you for joining us for our expert sessions. These are short webinars that take place every 2 weeks and last no more than 30 minutes, bringing you valuable insights from the industry experts. Today's session will be presented by Sonny Solanki, who's Senior Technical Manager at i-Gard. Sonny is an electrical engineer by McMaster University with 8 years of experience in protection systems and relays. Through his career, he has educated consultants and end users on the benefits of integrating electrical protection products into their designs to enhance personal and equipment safety. He specializes in providing commercial and technical support for various projects and applications, including high-resistance grounded systems, low-resistance grounded systems, hybrid HRG systems, ground fault and arc flash protection systems, resistor-based solutions, and personal protection products. We are excited to hear him today, and we appreciate your participation. Let's get started. Thank you, Sonny.
Thanks, Andrea, for the introduction. Today's presentation is going to be on voltage indicators versus absence of voltage testers and what you need to know. So just to start off, NFPA 70E is a standard for electrical safety in the workplace. And in the 2015 iteration in section 120.1, rule number 5, it indicates that an adequately rated portable test instrument can be used to test each phase conductor or circuit part to verify it is de-energized. This is where they test phase to phase and phase to ground to confirm absence of voltage. In 2018, they added an exception where an adequately rated permanently mounted test device can be utilized, which would be voltage test ports. In 2021, though, they further revised the exception and updated the requirement to be an absence of voltage tester. And then in 2024, they enhanced the clarity of Rule 7 by specifying that the test must be conducted at the actual point of work. In addition to that, you can see that the numbers of the clauses have also changed over the years. We started off at 120.1, and for 2018, we got to 120.5, and now we're looking at 120.6, particularly in the latest NFPA 70 iteration. So what's the difference between a voltage test port and an absence of voltage tester? Well, that's what this presentation's for, and we will go through all the details in this presentation. So to start off with, a voltage indicator basically has LED lights for each of the 3 phases as well as for ground, and indicates that there's voltage present when the LEDs are lit up, essentially. Then we also have voltage indicators and testers, which combine the LEDs alongside voltage test ports, which can be utilized to measure line to line and line to ground voltage on the front of the door. Then an absence of voltage tester is a permanently mounted unit that contains LEDs and a test button, which automatically tests the line to line and line to ground voltages to confirm absence of voltage with just the test button. So the main challenges with a voltage indicator is that its inability to confirm absence of voltage. So voltage indicators only show the presence of voltage, but cannot confirm the absence of voltage. There could be false results. The absence of illumination can result from various factors, including a malfunctioning LED, improper installation, or a defective device. This poses a risk if the indicator fails to properly detect de-energization, and that's why it cannot be used for absence of voltage testing. There's also a dependency on handheld tester, where a voltage indicator only detects voltage presence, requiring a handheld tester for measurement and confirmation of absence through the ports. There's a safety concern as well. Voltage indicators bring line voltage directly to the door, which poses a potential shock hazard, particularly when troubleshooting with an open door. Now, voltage test ports integrate the features of a voltage indicator and also have high impedance protected test points. The voltage presence is indicated through redundant LEDs, 2 per phase and 2 for ground. And we also have high impedance protected test points to measure voltage. Although the voltage seen on the bus is appearing at the door, the impedance path is really high, and therefore the current level is very low. The voltage indicator can go between 20 to 1000 volts AC or DC, and the test point can measure between 0 to 1000. In terms of troubleshooting, you can use this voltage test port for no power supply, no phase, under voltage, phase failure, harmonic analysis, as well as phase rotation. Further to this, in Annex 0.2.4 in NFPA 70E, if we look at 13, it says installing high impedance protected test points for voltage measurement through the door, reduce risk associated with an arc flash or electric shock hazard. Now, an absence of voltage tester is used to verify the absence of voltage in electrical circuits during a lockout tagout, where the equipment is de-energized and free from hazardous voltage before maintenance or repairs. This will reduce the risk of electrical accidents, which typically occur due to human error or device errors when it comes to voltage testing. So red LEDs would indicate that hazardous voltage is present, amber LEDs indicate that the test is in progress, and green LEDs indicate that absence of voltage is in fact confirmed. So this approach actually uses 2 wires per phase as well as 2 wires for ground in comparison to the 1 wire that appears for voltage test indicators as well as voltage test port. In doing this additional connection to the phases, what we can do is we can ensure that the absence of voltage tester is properly connected and has continuity. So we inject a small level of current through one of the leads, and as long as that signal comes back on the other lead, we can confirm that we're still connected to the 3 phases as well as to ground. So the test procedure for the absence of voltage tester is that it verifies the phase voltage lights are off, verifies the sensor leads are connected, verifies the energy level on the bus is low enough to conduct the test, and then verifies the voltage source is sufficient to conduct the test. Then it measures the AC voltage and DC voltage to confirm that it's less than 3 volts phase to phase and phase to ground. It checks that connectivity again, both in between the AC and DC test as well as after the DC test, and then it repeats that process once more on this stage here, and then the supervisory circuit validates that the tester is functioning satisfactorily and completing absence of voltage test, and then it provides the visual indication of whether there's absence of voltage or not. If there is absence of voltage, then you're going to get 3 green lights. If the absence of voltage test fails, it's going to give yellow lights indicating a caution situation. And this could happen because of a break in the connection or if there is voltage that is present. In CSA Z462, which closely mirrors NFPA 70E but is the Canadian edition, they also provide this exception in clause 4.2.5, exception number 2, where an adequately rated permanently mounted absence of voltage tester may be used to test for absence of voltage on the conductors or circuit parts at the work location, provided it meets the following requirements. So the AVT has to be permanently installed following manufacturer's instructions and conducts tests on the conductors at the point of work. It is listed and labeled for the purpose of testing for the absence of voltage. It tests each phase conductor or circuit component in both phase to phase and phase to ground, and it tests device is checked to make sure it works well with any known voltage source, both before and after testing for absence of voltage. The same exception can be found in section 120.6, rule number 7, and the same stipulations are dictated as well, which are closely mirrored on the Z462 side. So you can see here that in terms of an absence of voltage tester, it's able to tick off all of the boxes in relation to what an absence of voltage tester should do in comparison to a voltage indicator and voltage test ports. In this case, the absence of voltage tester is the only right solution to confirm absence of voltage in a system, aside from the traditional method of utilizing a multimeter. So UL 1436 is a standard which dictates the requirements for an absence of voltage tester as well as the design of it. So we'll just go through every step here. An absence of voltage tester shall be provided with the means for the user to initiate the test for absence of voltage. So we accomplish that with the test button. The AVT shall provide users with a visual indicator to confirm absence of voltage, and the visual indication shall be green. So those would be the LEDs on the front of the unit. A supervisory circuit has incorporated a secondary power source and shall have no internal failure that would impact performance. So the supervisory circuit is within the control box here, and the 2 leads AVTs basically have that supervisory circuit which confirms that we're still connected to the 3 phases and to ground. The AVT shall incorporate a supervisory test circuit to verify that the tester is functioning properly before and after the AVT performs voltage measurements. So again, that's also looping in through the supervisory circuit. And there's also visual indicators shall only illuminate green when all phase-to-phase and phase-to-ground voltages measure less than 3 volts AC or 3 volts DC. The AVT visual indicator shall not illuminate green unless the phase and ground leads are in direct contact with the circuit conductors being tested. And AVT visual indicator shall not illuminate green if a phase lead is connected to ground or the ground lead is connected to a phase conductor. So that's in the event of a ground fault condition that's existing on the system, even in the de-energized state. The visual indicator shall not illuminate green unless the secondary power source is operational. And also we have to comply with standard for functional safety in IEC 61508 and also achieve an SIL3 rating, which is a safety rating for the device, to ensure that there are no false positives, false negatives, and that the unit is able to withstand a large number of tests before it actually fails. So in having these requirements stipulated in UL 1436 and comparing them with respect to the voltage indicator and the test port to the absence of voltage tester, we can see that the voltage indicator and test portal is not meeting some of these requirements, particularly with respect to voltage pickup, and it doesn't have a supervisory circuit, and it's usually not complying with IEC 61508 and is not an SIL3 rated device. Voltage test ports are typically rated to UL 61010. So at i-Gard, what we've done is we've implemented both the voltage test port and the absence of voltage tester inside one mountable enclosure that is IP67 rated. We have the voltage test ports and the voltage test indicator, which can be utilized for online voltage testing, conforming to UL 61010. And at the bottom here, we also have our absence of voltage tester. We'll be able to conform to absence of voltage testing and meet the requirements in UL 1436 with an SIL3 rating. In addition to that, for when we're using a multimeter and online voltage testing, we've also put a known voltage source so that they can confirm that their multimeter is properly calibrated and is working as it should. So this is a combined unit, and we feel like there's an advantage both for online voltage testing and offline voltage testing with this product. In the future, we plan on getting higher voltage unit for this, for both the voltage test ports as well as the absence of voltage tester, so that we can create a safer environment and reduce the electrical shock and fatalities that have been occurring throughout the years in the past. So with the combination unit, you could see that we are able to satisfy a lot more than just using the absence of voltage tester. We can have voltage measurements and troubleshoot electrical equipment with the voltage test port, and also confirm absence of voltage with the absence of voltage tester. And with the known voltage source, it's just an added caveat in terms of being able to calibrate or confirm that your multimeter is properly calibrated. All right, let's head to our Q&A session, and we'll be fielding the questions right now. So Pratik, thank you for joining us today. What powers the tester when the equipment is de-energized? So inside the absence of voltage tester, there is a supercapacitor that is basically energized off of the bus when the system's energized, and when it's de-energized, that absence of voltage tester can hold its charge for up to 10 hours and can perform about 15 tests per charge. If the capacitor ends up discharging before you can perform the absence of voltage test, we also have a USB-C port underneath the unit which can recharge the supercapacitor within about 5 minutes or so. Where is the known voltage source derived from? It's a value of 3.3 volts, and it is coming from our control box and then transmitted via an IX cable, which is supplying both power and communication between the control box and the display unit on the front of the door. In doing it in this method, we're removing the hazardous voltage from being at the door and instead contained within the control box that is inside the actual unit that is being tested. So having a comparison of the way we do it today versus how we do this tomorrow, is it really required or just helpful? Well, it's not that it's a requirement, it's more so that there's an exception. You can still do this absence of voltage testing via your traditional method of testing with your multimeter, but what we've seen is that the electrical shocks and burns, fatal or non-fatal, haven't been decreasing over over a period of time, and a lot of the incidents were occurring during voltage testing. So in placing this product into your system, you can reduce time and also create a safer environment where you would reduce the probability of a hazard by having this absence of voltage tester perform the test between the two phases as well as phase to ground before you're even opening the door. So a question from John Whipple: what sets your AVT apart from Panduit's AVT? Both AVTs are fairly similar. The only difference is Panduit's AVT is using a battery, and the battery, if it discharges or doesn't have any power, then it could be an issue. Whereas the supercapacitor, we can charge that up through the USB-C port underneath the device, and that would be the main thing that sets us apart. We are also working on higher voltages, so eventually we will be releasing those, and that would provide us with a bit of an edge as well against their offering in particular. If you have any other questions, so one of the competitor product requirement is to use a 10 mega ohm meter for test ports. Is there any limitation on i-Gard's AVT? So the 10 mega ohm meter for the test port, those are in regards to the test ports. Remember that the AVT is different and it doesn't have test ports. We are getting the voltage to our control box and it's not appearing on the front of the enclosure because we're transmitting the information from the control box to the AVT via the IX cable that we're utilizing. This reduces the hazard for that voltage to be on the front of the enclosure, and therefore there's no real requirement for any form of resistance. On our test ports, we have a very, very high impedance. I believe it's around 10 mega ohms between our test ports for our voltage test port. All right, thank you all for joining us today on this expert session, and please look out for our next expert session, which will be on our insulation monitoring relays, and that will be conducted on May the 20th. Thank you for your time.